Hey everyone, it's time to talk about particles again. Last week we learned about the Lennard-Jones potential energy, which describes the way that two neutral particles interact. The Lennard-Jones potential allows us to understand a little bit about how two particles behave. And if we know how two particles individually behave, we can potentially use that information to figure out how lots of particles behave, huge collections of particles like you find in most cases. And we're going to do that today. Specifically, we're going to look at how we can use what we know about the Lennard-Jones potential energy to learn something about the bond energy of large amounts of a substance. Now, we've never actually talked about the total amount of bond energy in a substance before. Up to this point, bond energy has just been the thing that changes when a substance undergoes a phase change. We've never said, oh, this system has 200 kilojoules of bond energy. But understanding the Lennard-Jones potential actually allows us to do something like this. First, I'm going to give you a definition of bond energy in this context, and then we're going to talk about what it means in terms of the Lennard-Jones potential. The bond energy of a solid is just the amount of energy that the solid has when it has zero temperature. Now, why is this? Well, we've seen that temperature and thermal energy are directly related. When temperature goes up, so does thermal energy. It probably is not too surprising then that if temperature is zero, then the thermal energy would also be zero. So imagine a system of particles, a substance with zero thermal energy. If it has zero thermal energy, there's only one other kind of internal energy it can have. It's bond energy. And so if we could compute what the energy of a substance was at zero temperature, we could compute the total bond energy of the substance as a solid. Now, in real life, it's not actually possible to truly cool something down to absolute zero. We can only get substances very close. But we can still imagine what would happen if we cooled the particles down to absolute zero. Soon we're going to see how thermal energy works for individual particles, but I'm going to give you a little preview now. Thermal energy in particles is at least partly associated with the movement of particles. The faster particles are moving, well, the more thermal energy they have. So how fast do you think particles are moving if they're at zero temperature? Well, the answer is they're just not moving at all. So how does that help us better understand how bond energy works for pairs of particles? Well, to do that, let's take a look at the Lennard-Jones potential. Okay, so here's the Lennard-Jones potential. Now, you might look at this and be like, well, what information do we have that allows us to use this? To see, let's think back to our definitions. If two particles are sitting close to each other, they will be interacting according to the Lennard-Jones potential energy. The amount of potential energy they have will just be described by where they are on the Lennard-Jones potential energy graph. But what does it mean to say that the particles are at zero temperature? Well, we said that for particles to be at zero temperature, they have to have no kinetic energy. So we know that the particles have no kinetic energy, but does that mean we know how much potential energy that they have? Well, the answer is actually yes. Let's imagine that we had two particles who were not moving and were sitting about 1.5 times their particle diameter apart. On this graph, that's right here. Now, what would happen if we then just let these particles go? Well, this potential energy graph tells us exactly what happens. The particles would feel a force in the direction of decreasing potential energy. They'd start to move down this hill. But what happens if the particles are moving? Well, they no longer have zero thermal energy. This is true almost anywhere that you put the two particles. So how can we then know how much potential energy the particles have if they have zero kinetic energy? Well, it turns out there is actually one place that the particles can sit such that if they have zero kinetic energy, they'll just stay there and not move. Where is that spot? Well, it's right here at the bottom of the well. The force right at the bottom of the well between the two particles is exactly zero. It doesn't push the particles to the left or push the particles to the right. And so if you have two particles at zero temperature, there's only one place that they can be sitting, right here at the bottom of the well at their equilibrium distance apart. In other words, if we cooled two particles down to 0 degrees, we could figure out exactly how much energy that they would have. They would just have negative epsilon of potential energy and 0 kinetic energy. So there's our answer. For a single pair of particles at 0 degrees Kelvin, the particles will have 0 kinetic energy and negative epsilon of potential energy. We said that the amount of energy that the particles had when they had 0 thermal energy was equal to their bond energy. So we know the bond energy of these particles. It's just negative epsilon. Now, earlier in this course, we said that changes from solid to liquid and liquid to gas resulted in positive changes in bond energy. Now, if you've taken chemistry, this may be the opposite of what you've been taught. And now we can start to see why this is the case. Two particles in a solid are going to be sitting pretty close to the bottom of this well. They'll have negative epsilon of bond energy. But now imagine two particles in a gas. The two particles in a gas are so far apart that they're just off the graph. They're not really interacting anymore. How much potential energy do those particles have? Well, they have 0 because the Lennard-Jones potential energy goes to 0 as you get far apart. And so in order to go from a solid to a liquid and then to a gas, you need to push the particles up the well. They have to escape. And that's why the changes in bond energy for solid to liquid and liquid to gas are positive. So why does this information about the Lennard-Jones potential help us? Well, it helps us because we now know how much energy is stored in a single bond. So if we want to know how much energy is stored in all the bonds in a substance, what do we need to do with this number? Well, we just need to multiply the amount of energy in each bond by the number of bonds in a substance. Now, in DL, you're going to see where this comes from, but we actually have a model of how many bonds a substance with a very large number of particles has. It's shown here. N is just the number of particles. It's probably not surprising that the number of bonds a substance has depends on its number of particles. The 6 comes from thinking about how many bonds a particle will have to its neighbors. On average, in a solid, particles have about 12 bonds to their neighbors. So why the 6? Well, the 6 comes because if we just multiply 12, the number of bonds per particle, by n, the number of particles, we actually end up with twice as many bonds as there actually are in the substance, because each bond involves 2 particles. And so, in order to calculate the number of bonds in the substance, we just divide by 2. 12 divided by 2 is 6. So our model for the bond energy of a solid just looks like this. It's 6n, which is the number of bonds that the substance has, multiplied by negative epsilon, which is just the amount of potential energy that each of these bonds has. Now, the key thing we have to remember when working with this model is that it only works for very large numbers of particles. A typical amount of particles that we're talking about in a problem is a mole of particles, Avogadro's number of particles. This is a case where we can be sure that our model applies. The number of particles is so large that the approximation that we made about the number of bonds per particle being 12 works just fine. But this stops working when the number of particles get a lot smaller. 12 being the number of bonds that a single particle has comes from thinking about a particle in the center of a substance. It's surrounded on all sides by other particles, and it has roughly 12 bonds between them. But what happens if you're a particle that's way out on the edge of a substance? Now you're not surrounded by particles on all sides. Maybe there's just a huge empty void on one side. And so you're going to have less bonds. Now, when the number of particles is big, this turns out to not be a very big deal. But when the number of particles shrinks, this approximation starts to get worse. Imagine that you only had 6 particles. It's clearly impossible for the particles to have 12 bonds each. There isn't even 12 other particles to form a bond with. When you get to these really small cases, you may have to start doing the calculation explicitly. Remember that the basic model of bond energy still applies. The bond energy of a substance is just equal to the bond energy of a single bond multiplied by the number of bonds. For a small number of particles, this is still true, but instead of just making an approximation, you may have to look at each individual particle and take into account the amount of energy in all of its bonds, instead of just sort of assuming that each particle has the same number of bonds and they all have the same amount of bond energy. Now, you'll see an example of this in DL, and we'll do some practice problems. But the key thing to take away is that both the small scale model and the large scale model come from the same place. We're just looking at how much energy each bond in our substance has and adding them up. When we have a very large number of particles, we can generally assume that each particle has about 12 bonds to its neighbors, and the total number of bonds in the substance turns out to be 6 times the number of particles. To get the bond energy from that, we just multiply by the amount of energy in each bond. For a solid, this is negative epsilon. And again, in the small case, we're basically doing the same thing. We're just not invoking any approximations. We're not saying every particle has 6 bonds to it. We're actually looking at the individual particles and counting the bonds and making sure that they all have the same amount of energy. Now, there's an important thing that this model does not tell us. We just saw what our model for the bond energy of a solid is. The bond energy of a gas is just 0. The particles have been moved so far apart that the Lennard-Jones potential just doesn't have an effect anymore. The particles have 0 potential energy as a gas. But what about the bond energy of particles in a liquid? To be clear, our model doesn't answer this question. It doesn't tell us how much the bond energy of each particle changes when the substance goes from a solid to liquid, or for that matter, from a liquid to gas. So we don't have a model for this. However, understanding where the bond energy of a large number of particles comes from is actually really powerful. Now, in the next video, we're going to start talking about thermal energy. Now, I said at the beginning that particles with no kinetic energy have no thermal energy, but this is only half the story. You might take this and say to yourself, well, that means that thermal energy is just kinetic energy. And the more kinetic energy that two particles have, the more thermal energy the two particles have. This second part is true, but the first part, the fact that thermal energy is just kinetic energy, turns out to be not exactly true. This becomes a little bit tricky, but we'll see how this all works in the next video. That's all for now. See you in the next one.